Alright, day 3. The new concept we're going to tackle is deciding whether a function is even, odd, or neither. Now we're talking about symmetry here. We're not talking about the degree, which would just be like, oh look, the degree is 4, yay. No, it's more than that. We're talking about the shape of the entire function. Now, just visually, I need you to understand that if a function is even, it will be symmetric around the y-axis. In other words, the y-axis will split it right down the middle. If a function is odd, then it will be symmetric around the origin. Alright? That means that if I take the graph and I rotate it upside down, it will still look the same, regardless. Okay, so that is odd when you can rotate it upside down and it still looks the same. So that's visually. So for example, this would be odd. This would be neither. All right, it looks almost even, but it's not the y-axis. It's not the axis symmetry. This would be even, y-axis symmetry. Okay, this would be odd because it has a rotational symmetry around the origin. See how it still looks the same? This would be odd, same thing. And this would be even. Y-axis splits it right down the middle, so that would be even. Now, on the other hand, when we another thing about even functions is all the exponents will be even. Now remember that 0 is even, and also remember that if I have a number like 5, that's the same thing as 5 to the 0 power. But for an even function, all of the exponents will be even. And then for an odd function, all of the exponents will be odd, keeping in mind that something like 5x is like 5x to the 1 power, which would be odd. Okay, so that's one deal. Now we're supposed to prove this algebraically, which I will get to in a second. Okay, proving algebraically takes a little bit of work, but even before you start proving it, you should know whether or not it's even or odd, and then you can go ahead and prove it. So let's start by just saying whether it's even, odd, or neither. So for example, this one, alright, I think I will use purple. Alright, let's see. I see even and odd, so this one's going to be neither. I see 4 and 2, so I know this is going to be even. 5 and 3, I know this is going to be odd. Okay, 4 and an invisible 1, okay, so that's even and odd. So that's a mixture, so this one's going to be neither. Okay, 4 and 2. All the exponents are even, so that means this function is going to be even. 5 and 3, the exponents are all odd, so I know that this function is going to be odd. So I know right from the start whether or not it's going to be even, odd, or neither. But that's not enough. We're supposed to prove it algebraically. Now here's how you prove it algebraically. What you do is you plug in negative x into the function. If you plug in negative x, in other words, if you replace all the x's with negative x, if you end up with the same function, then it's even. If you end up with the opposite function, then it's odd. Alright, same function even, opposite function odd. Okay, so let's do that. Now we know this is going to be neither. So this is what I like to do. We have the same function here. Let's go ahead and make the opposite function. So let's see, opposite. All right, because we have to show that we're going to get neither of these. So we have the original function. Now we need the opposite. Look, when you want the opposite function, all you do is you multiply everything by -1. All right, so if I do that, I'm just going to get negative x to the fourth power and minus x to the third power. Okay, so this red function here, this is the opposite function. Okay, and see, officially we will call that opposite function, we just call it negative f of x. All right, so that's the opposite function. Now let's plug in negative x and see what we get. So if I plug in negative x, I better zoom in because it was getting too hard to see what I'm doing. Okay, so here I'm getting ready to plug in. All right, so I've got my parentheses to the fourth power, parentheses to the third power. Okay, and I'm going to plug in negative x. Okay, now if I do negative x to the fourth power, because that's even, that's going to turn this completely positive. So this is just going to give me x to the fourth power. All right? When you raise a negative to an even power, you get a positive. So positive x to the fourth power. Now, if you raise a negative to an odd power, it stays negative. So this is going to become minus x to the third power. Okay? This negative is not going to go away. So I have this. All right? Now comparing these three functions, all right? Comparing the function that we got by plugging in negative x and comparing that with the original function and comparing that with the opposite function. All right? All three of these are different. All right? Then none of them are exactly the same. So that's how you know that this is going to be neither. All right? So if you were asked to explain, you would say neither because all are different. Okay, let's take a look at number 2. Now, we know this is going to be even right from the start. So what we have to prove is that we will get the same thing back when we plug in negative x. So let's just go ahead and do our plugging in. So here's my parentheses to the fourth power plus parentheses squared. Inside of here, I will put my negative x. Okay, so let's see what we get. Well, a negative to an even power, the negative goes away, so I will just have x to the fourth power. And again, here we have a negative to an even power. That negative is going to go away. So I will just have plus x squared. Okay, so let's compare this with this, the original function. All right, the original function and the function that we got when we plugged in negative x are exactly the same. So that proves that they're even. Okay, if the original function, if you get the original function back again when you plug in negative x, that proves that it's even. Okay, let's look at number 3. All right, I'm picking up a little speed now. We know this is odd. So because we know it is odd, we know that it should be the opposite function is what we should get. So let's look at the opposite function. Let's look at the opposite function is negative f of x. In other words, if I took this function and I multiplied everything by negative 1, I would get negative x to the fifth power minus x to the third power. This is the opposite. All right, and maybe I'll just label it. Okay, this is the opposite. Okay? So if I plug in negative x, I should get this. Let's try. So if I do f of negative x, you know what? I like to make this green just so it looks a little different. So I'm doing to the fifth. I'm doing to the fifth power, and I'm doing to the third power. Okay, and please understand, I'm looking at this original equation right now as I build this. I'm not looking at the red. I'm looking at the original equation, and let's see. So I'm going to put in my negative x like this. Okay, but if I take a negative value and I do an odd exponent, the negative doesn't go away. So I'm just going to have negative x to the fifth power. This negative is not going to go away. It's going to stick around because this is an odd power. So I'm going to have negative x to the third power. So this is what I would get. And take a look. Alright, I plugged in negative x and I got this. But if I look at the opposite function, I get this. And take a look. The opposite function is the same thing. Alright, and that proves that it is odd. Alright, if you get the same thing as the opposite, it proves that it's odd. Okay, look at number 4. Now this should be neither. So I'm still going to do the opposite, even though I know it's not going to match either one of these. So I'm going to do the opposite. And again, the opposite is what you would get if you just multiplied everything by negative 1. So that's going to give me negative 3x to the fourth power plus 4x. Okay, so this red here is the opposite, and yeah, I think I'll label it opposite. Okay, so I've got the opposite function, I've got the original function. Now, when I plug in negative x, it should be different from both of these, and that's what makes it neither. So, but this is how you prove it. You prove it by plugging in negative x everywhere. So here's my negative x, negative x, negative x. So this is going to give me, when I do an even power, this negative is going to become positive. So it's just going to be 3x to the fourth power. But there's no exponent here, so this negative is not going anywhere. So this negative is going to come out front, but look, there's already a negative there. So it's going to be like the opposite of a negative. When you put these two negatives together, it will become positive. Alright, it's like negative 4 times negative 1. It's like a negative times negative is a positive. So I'll have a positive 4x. So this is what I get when I plug in negative x. So when I compare this and this and this, I see that none of them are exactly the same. They're all different. Alright, so I can just say all different. So neither. Okay, let's take a look at number 5. Alright, so looking at number 5, this is supposed to be even. So I'm expecting to get it to be the same as the original function. So we can just go ahead and jump in by substituting negative x and see if we get the original function back. So here we go. If I substitute negative x, Well, a negative, when you have an even power, a negative will become positive. So this will just become 5x to the 4th power. Negative goes away. Again, even power, so the negative goes away. So it'll just be plus 3x squared. Okay, so I have this, and when I compare that to the original function, I see that they are the same. Okay, so I could write same as original. So even. Okay. And finally, number 6. This should be odd, so I'm expecting it to be the same as I'm expecting for it to match the opposite of this when I plug in negative x. So let's definitely do the opposite, which would be like this, negative f of x. Okay, so the opposite, again, one more time, the opposite is what you get when you multiply by negative 1. So that would be negative 6x to the 5th power, all right, plus x to the 3rd power. So this red here is the opposite. And this is what we're expecting to get when we plug in our negative x. So let's take a look. So f at negative x. For some reason I like to use green when I do this. So I've got 6 parentheses to the 5th power minus parentheses to the 3rd power. And inside of there, I'm going to put negative x. All right, let's see what happens. Odd power, so this negative is not going to go away. So it's going to kind of come out front and become negative 6x to the 5th power. This negative is not going to go away because it's odd. So this negative is basically going to come out and it's going to still be there. So I've got a negative times a negative is a positive. So it's going to become plus x to the 3rd power. So this is what I get when I plug in that negative x. Now compare that to the opposite. Okay, negative x to the 5th plus x to the 3rd, negative x to the 5th plus x to the 3rd. The opposite is the same thing as what you get when you plug in negative x. So that tells us that it is odd. All right, now officially the way I would say that would be, I would say the opposite equals what you get when you plug in negative x. So odd. All right. Same as opposite. All right, that is how you prove algebraically that something is even, odd, or neither. Now, just glancing at these, you should be able to quickly tell if they're even, odd, or neither. This one, what do you think? This one is neither. It looks a little bit even, but it's got to be the y-axis right down the middle. So this is neither. This is a trick question. This is actually two things, all right? This is both even and odd. All right, this is a tricky one. This is even and odd. It's even because the y-axis is the axis of symmetry. All right, the y-axis does split this right down the middle. It's odd because if I were to take this, all right, see here I'm copying it, all right. Now if I were to take this and rotate it upside down, like this, okay, hopefully you can see that it looks exactly the same. Whether it's right side up, upside down, it still looks the same. So that makes it odd as well. Okay, so it's even and odd. Very interesting. This one is going to be neither. All right, it does not look the same when we turn it upside down. And the y-axis does not split it down the middle, so that's a neither. This one is odd. I feel like I've seen this one before. If this one has symmetry around the origin. All right, it's perfectly balanced around the origin. Turn it upside down, still looks the same. This is going to be neither. All right, it does not look the same if I turn it upside down, and the y-axis does not split it down the middle. This is going to be neither. All right, it will not look the same if I turn it upside down. Now, if I look for the middle of this graph, this is the center of this function. If I rotated this graph around this red point, it would look the same. But it's got to be the origin. Okay, if the graph were moved over to where this were sitting at the origin, then it would be odd. Okay, number 13. This is neither. All right, it would not look the same if we turned it upside down, and the y-axis does not split it down the middle. This is even. Y-axis splits it right down the middle. All right, is that it? I feel like there should be one more right here. Guess not. Okay, now the rest of this, I believe, is sort of review. Okay, domain. And please remember that the test will have review questions on it, so be ready for this. The domain is how far it goes left and right. All right, I think we're supposed to assume because of the way, well, this one kind of stops right here. Man, this is ambiguous to me. This graph appears to actually stop right here, and I think we're supposed to assume that it keeps going here because of the way it runs off the graph. I'm going to go with that interpretation. So with that in mind, the domain is going to be -8 to infinity. Okay, left -8, right forever. Okay, so -8 to infinity. That's funny because it looks like an 8 and a sideways 8. I actually think this one is going to be a boxy bracket instead of a parentheses, because it clearly hits 8, -8, boom. So the -8 will be included. Now the range, better zoom out a little bit. The range is y values, okay? So domain, that was x values, so we did left to right. The range is y values, so we will go bottom to top. How low does this graph go? Well, I'm putting these arrows on here to show that I think this goes down forever in this direction. So that's -infinity. How high does it go? All right, so I've got a -infinity to something. This is the highest point right here at 8, so -infinity to 8. All right, now end behavior. Now with this being a dot here sealed off, not sure we can even really talk about the end behavior. But I'm going to go ahead and say the end behavior just like I would if this were an arrow as well. So the end behavior would be basically on the left it falls, and on the right it falls. Okay, so that would be like this. Alright, as x approaches negative infinity, f of x approaches negative infinity, falls. Alright, as x approaches positive infinity, f of x approaches negative infinity. Alright, falls, falls. X-intercepts, which are also the number part, would be called zeros. But the x-intercepts, I see two of them. One of them is -7, 0. And the other one is +7, 0. Y-intercepts, I only see one. There's my y-intercept. And that is 0, 4. Maximum. Now I talked about this being the highest point reached on the graph. If I go ahead and look at that as an ordered pair, okay, so this would be the maximum. So that's 5, 8. Okay. Alright, 5, 8. That is the absolute maximum. Okay, and I don't seem to be breaking it down as absolute versus relative. But so I'm just going to add it on, okay? Just go ahead and add this on your paper for me, please. So that was the absolute maximum. Now let's talk about the relative. Whoa. Let's talk about the relative maximum. Because there's one of those. The relative maximum will be the one that's not quite as high as the absolute maximum. So this would be the relative maximum at -6, 6. Okay, so let's put that down as the relative maximum. Okay, and this is I should have changed this question to something else. Let's see. Let's go ahead and change this to minimum and absolute minimum. All right, let's pretend that these were the questions, because this is more like what it should have been. Okay, so the minimum, you know, I guess I should be saying the relative minimum versus absolute minimum. Is there a relative minimum? Why, yes, there is. I'm glad you asked that. There is a relative minimum right here. It's the y-intercept, actually. All right, 0, 4. It's not the absolute minimum, because it's not the absolute lowest point on the graph, but it's the lowest point in its little area. So there's a relative minimum at 0, 4. Absolute minimum, there's none. All right, because it goes down forever. Now, find f at -3. Okay, look, any value inside of this parentheses is an x value. And so you're being asked for the y value that goes with it. So if I go to an x value of -3, and then look around to see where the function is. Okay, so here I am at -3. I look up, bam. I see the function is here at 5. So that means at an x value of -3, the value of the function is 5. It's the y value. Okay, now increasing and decreasing intervals. Okay. Alright, I really wish we had done an arrow over here. But okay, fine, it's a dot. Increasing. The increasing interval, I'm going to go ahead and color in green. So it's going to be increasing from here to here. And then I'll show the decreasing part in red. So that'll be decreasing. And then it will be increasing, all right, because increasing is going uphill. So from left to right, I went uphill, downhill, downhill. So everywhere I was going uphill was increasing. Everywhere I went downhill is decreasing. Okay. So the graph is increasing from -8. Oh, by the way, these are all x values. Even increasing, decreasing, they're all x values. So it was increasing from an x value of -8 to an x value of -6. It's like from here to here, it was increasing. So -8 to -6. And then it was also increasing from here to here. All right, from 0 to 5, all x values. So that's where it was increasing. Now it's decreasing, okay, look at these red. But again, it's just the x value. So it was decreasing, all right, let me start these over. It was decreasing from here to here, okay, from -6 to 0. And it was decreasing from here on, okay, because this goes forever that way. So it's decreasing from 5 to infinity. It keeps on going to the right. All right, so those are decreasing intervals. Okay, now we need to review our factoring skills. Wow, well, I'm seeing that this is 4 terms, so I probably should try grouping on this, if you can remember that. Grouping works like this. I'm going to group the first 2 terms and the second 2. Better zoom in a bit. Looking at these first 2 terms, I factor out the GCF, the greatest common factor. Both of these are divisible by 4 and x. So I will pull out 4x as the GCF. Okay, and both of these are divisible by 3. So I'll pull that out. That is going to leave behind x plus 2. Okay, now these x plus 2's are themselves a GCF, which need to be pulled out front. So I pull this x plus 2 out front. That is going to leave behind 4x plus 3. The 4x and the plus 3. Notice that this is not squared or anything. So that's it. Alright, we did that one by grouping. Alright, look at number 26. Look, the first step of factoring is to look and see if there's a common factor. I see one here. Everything's divisible by 2. So I'm going to do that. So I'm going to pull out a common factor of 2. That's going to leave behind x squared plus 11x plus 30. Okay, so now I have to keep going and factor this further. So x squared is going to factor as x times x. 30, well, you know, 30 is very likely to be 2 times 15, or it could be 6 times 5. Alright, but technically it could even be 1 times 30. Alright, it could also be maybe 3 times 10. Alright, these are some things that give me 30. Now, because this has a leading coefficient of 1, I can immediately start to look for the 11 right here. So which one of these pairs could give me an 11, either by adding or subtracting? Yeah, only the 6 and 5 could make 11. All right, I can only use this shortcut when the leading coefficient is 1. But it was, so I will. So 6 times 5. Now the middle needs to be 11. So right now, inner, I have 6x. Outer, I have 5x. To make positive 11, I need positive 6 and positive 5, like this. And a positive times a positive is a positive, so that works out. That means I'm done. This is completely factored. Okay, let's take a look at number 27. Any common factor here on 27? No, that's prime. Okay, so let's go straight for binomial times binomial. Now 3x squared, that can only be 3x times x. 14 is either going to be 2 times 7 or 1 times 14. That's it. Let's try the 2 times 7 first. Okay. Now inner, I have 2x. Outer, I have 21. Alright, I'm multiplying. The inner plus the outer has to give me the middle, so I'm shooting for 13. Is there any way to get 13 out of 2 and 21? No. How about no? Well, before I throw out the 2 and the 7, let's try putting them the other way. Let's try 7 and 2. Okay, now inner, I have 7x. Outer, I have 6x. Is there any way to get 13 out of that? Well, yeah, if these were both positive, that would make 13. So that would be like this. And positive 7 times positive 2 makes positive 14. So, kabam! We're done. Okay, so that's the answer. Alright, number 28. Again, there is no common factor. So I will go ahead and go for a binomial times a binomial. 3x squared can only be 3x times x. 5 can only be 1 times 5. So let's do that. Inside I have 1x. Outside I have 15x. I'm trying to get this middle of negative 2. So far it's not looking good for me. However, I know that it makes a difference if I rearrange these. So instead of doing 1 and 5, I will try 5, 1. Now inner, I have 5x. Outer, I have 3x. I'm trying to get negative 2. I can get negative 2 if I do a negative 5 and a positive 3, which would translate into negative here and positive here, all right? Because positive comes from the outer. So, also, negative 5 times positive 1 is negative 5, so that works out as well. So that's it. That means this is the answer. Okay. I think I should erase some more. Maybe later. Alright, what else you got? Solve by a factoring using the method of your choice. Yeah, notice on these problems we just factored and stopped. I didn't set these equal to 0 or anything. That's because these are not equations. Alright, there's no equal sign anywhere. Alright, it just says factor completely. It does not say solve. Alright, as opposed to this. You see it has an equal sign. That's a clue that we're going to be going all the way down to like x equals something. Also it says solve, which is another clue. It says solve by factoring using the method of your choice, but it said factoring, so that seems like the method right there. So I'm I'm not really sure what that was all about, but let's just do the problem. X squared, well that can only be x times x. 25, normally I would think 5 times 5. In fact, I don't think this is factorable. So these are bad directions. Yeah. It shouldn't say solve by factoring. It should say solve using the method of your choice. Like that. And this is unfactorable, so yeah, factoring is not working out for us. Instead, we could use either the quadratic formula or the difference of completing the square. I'm going to use the quadratic formula. No, I'm going to complete the square. Completing the square is easy to use when there's no number in front, when the leading coefficient is 1, and when the middle term is even. Since we have both of those, why not complete the square? Remember, completing the square worked like this. We would subtract the 25 from both sides. So we'd have x squared minus 8x, leave a space, equals negative 25. And then we complete the square by doing half of this squared. So half of this is 4, square it, you get 16. Alright, I'm going to have to put that 16 on both sides to keep the balance. Now, if we did this correctly, then this should factor as the same thing twice. In this case, x minus 4 times x minus 4. Whoa. Okay, meanwhile over here we have negative 9. But I can write this more compactly as x minus 4 squared equals negative 9. Then it's time to take the square root of both sides. Okay, don't forget your plus or minus. So that's going to give me x minus 4 is equal to plus or minus, and this will be 3i. Okay, because this is like I radical 9, which is 3i. Okay, so plus or minus 3i. Then we must add 4 to both sides, being careful to put that 4 in the front. So I'm going to have x is equal to 4 plus or minus 3i. Alright, that's it. No wonder it was unfactorable. It's an imaginary solutions. Okay, what else you got? So that was 29, so yeah, 30. No matter what I do, I probably want to move this 6x over to the left. So that's going to give me 3x squared. Well, you know what, let me be precise. I'm not just moving it, am I? I'm subtracting it from both sides. So that is going to give me 3x squared minus 6x minus 1 equals 0. I could still complete the square if I wanted to, but because this has a 3 here in front, probably the quadratic formula would be a better choice. I'm not sure if it's factorable, but it's not looking promising. I'm going to use the quadratic formula, which says that if I have ax squared plus bx plus c equals 0, then x is equal to opposite of b plus or minus the square root of b squared minus 4ac all over 2a. There's my quadratic formula. So there's my a. Okay, okay, a is 3, b is negative 6, and c is negative 1. Now in the past, I have encouraged you to do the discriminant first. Okay, your b squared minus 4ac first. So let's do that. B squared minus 4ac. So using my handy dandy calculator, okay, maybe I can scoot over just a bit. Yeah. Okay, so I need to do b squared minus 4ac. So b squared, I've got negative 6. So if I square that, I will have positive 36. I encourage you to square that in your head, because in your head you know that it's positive. If you just type it in your calculator, you might mess up and think it's going to be negative. So 36 minus 4ac. So that's 3 and negative 1. Okay, so your discriminant is 48. So when you go to do your quadratic formula, okay, so here we go. X is equal to opposite of b. Alright, b is negative 6, so I'm going to do positive 6. Plus or minus square root. Alright, all over 2a. Well, a is 3, so 2a is 6. And this part under here is the part that we found in the first place to be 48. So we got 48. Do not type this whole thing in your calculator. The only thing I want in your calculator is the square root of 48. Okay, so if I do the square root of 48, that's 4 radical 3. So that gives me x is equal to 6 plus or minus 4 radical 3. Okay, over 6. So far so good. We just need to reduce this. And whenever I reduce this, I like to make a heart to remind me what to do. Okay, a heart around these three things. You can only reduce if all three of these are divisible by something. If there's a number that goes evenly into all three, you must divide. So these are all divisible by 2. It's got to be all or nothing. If this was a 5 instead of a 4, I could not do anything at all with the 6's. Alright, so this is going to become maybe I should bring it over here somewhere. So this is going to become 3 plus or minus 2 radical 3 over 3. And guess what? This is the final answer. Notice I cannot cancel out these 3's. Alright? It's all or nothing. You can either divide all 3 or you have to leave it alone. Alright? Alright, and that is the end of this lesson. I hope it was helpful, and I hope you weren't just copying off of me. Please make sure that you can do these by yourself. Never watch the video with a pencil in your hand. I'll see you on the next video.